Welcome to GJordan. My name is Bolus Harb, and in this talk I will describe, sorry, I have to always speak to the mic. In this talk I'll describe some of the technology, algorithms, and challenges behind Google search by voice and related products. In the main room there is the Google App Engine Part 2, so just make sure you're in the right room. So voice search was born in the research group at Google New York. It is an example of how we use research to build real products and solve problems we see in the field. And it's driven by our users. So we don't do research just for the sake of research. We want to build products and we want to benefit our users. So what is new here? Speech technology is available in many places. Why did this need to come out of research? What are the challenges we faced building this product? So I'll try to emphasize, try to answer some of these questions, give an overview, and emphasize the practical aspect of research. Okay. So before we delve into the technology behind Google search by voice, let's describe what the product is all about. The goal of the product is to recognize any search query you speak to the phone. It is a big step forward for speech recognition systems. So to date, people have been very successful in domain-dependent applications. So for example, we have Google 411 that lets you search for a business given a city and state. So you call 1-800 Google 411, it asks you which state, and then you give it the state. Based on that, it reduces the search space. It asks you which city, you give it the city, and based on that, it reduces the search space again to the businesses, and then you give it the business name. In contrast, Google Search by Voice lets you search anything: businesses, songs, electronics, books, websites. The aim is to search the web by voice. So a domain-dependent solution here will limit the utility of this service. So technically, it's a very challenging task compared to systems we have worked on before. Imagine you have multiple applications, one for searching businesses, one for searching products. That doesn't work. We want one place, click one button, and you speak anything you want, just like you would do with a search engine. So why is this challenging? So first, the vocabulary of search terms is really, really big. It's much bigger than the English language or just one language. Imagine product names, city names, states, and so on. And I'll give an idea of how big this is during the language modeling section. And then deploying a service like this, even just in the United States, also highlights the fact that we have to contend with variability in accents. So the way a person speaks in Boston is different than the way in New York, which is different than the way to speak in Louisiana, and our acoustic models have to take that into consideration. It's also a speaker-independent system. People speak to our servers from all over. It's not like having one software on your computer that adapts to your voice. So this is speaker-independent and accounts for variability in accents. And one of the key uses for the service is to search while you are mobile. So you're walking on the street, you're driving your car. This presents another significant challenge for making the system robust against background noise, and not just one type of noise. So we actually model different types of noise in the system. So the noise in your car is different than the noise on the streets of New York. Okay, and now what makes this seemingly intractable problem possible at Google? And one part is the technology stack is built from the ground up. It's a completely homegrown solution, and that's important for us because we can we control every part of the technology. We write it, we control it, we can adapt to it, we can change it when we find problems, we can fix them. We have access to lots of data, and we'll talk about how we train our language models. Essentially, we train them from the Google query stream. And finally, to do this kind of productive research with lots of data, you need computing power. And fortunate enough to work at Google where we do have the computing power to do this. Okay, and we will touch base upon these during the talk. So one question you may ask, where can I find Google Search by Voice? And it's available on various phones, iPhone, BlackBerry, Android. So I'll give a demo of it right now. Switch, please. Okay. International Space Station. Okay, hopefully the network helps. International Space Station. let's try something else. A Space Odyssey 2001. So this is the name of a movie. It didn't get it completely, and it gave me a few options. So I can click on the first option. And in fact, I have the name of the movie wrong. The movie is called 2001, A Space Odyssey. But the search results get it right. And notice how I say 2001, and you get the number 2001. Another example.
Need for Speed.
Sorry?
Need for Speed.
Need for Speed. Need for Speed. Sorry, I think I'm having network problem. But essentially what happens here is, as you're speaking, we are sending audio packets to the server while you're speaking and recognizing in a streaming fashion. And then we return to you the transcription followed by the search results, because the payload of the search result is higher. So I'll give one more, which is an address query. Chelsea Market in New York. Oh, sorry, I didn't even press the button. Chelsea Market in New York. Chelsea Market in New York, and we recognize you are looking for an address, and you get the location. In maps, you can call the number, or you can get directions. Okay. So, switch. So what's more interesting is how other people use this, and I'm going to break out a little bit from the presentation and show you something I would have never expected people use the product for, and I was actually many years of research so that the following can happen. So this is a game. Kids fill their mouth with marshmallows, and they have to say the words chubby bunny. And if Google Voice Search recognizes chubby bunny with the maximum number of marshmallows, then the person wins.
This is how it works. Each person would say chubby bunny into the speaker like this. Chubby bunny. Then it would say working care. If it says that, then they get the point. It doesn't? No. Okay.
So I'll go first.
All right. Let's start with 2.
Chubby Bunny.
Okay, it's working. Yeah, that's great. That's kind of good. Okay. Come on, TJ. Chubby bunny. It's working. Oh!
4.
Chubby bunny. It's working. It's gonna get down. Working.
It's up to you, DJ. With 4.
Chubby bunny.
So with 4 marshmallows, it's difficult. Okay. So of course, that's not how we planned the product, but it was very interesting to see years of research used to enable Chubby Bunny. Okay. Since we launched in US English in November 2008, we started the process of internationalization. But even before that, even though our acoustic model can handle variability in accents in the US, British English, Australian English, and Indian English are actually quite different, and we have to build adapted acoustic models. So we take the acoustic models and we adapt them with standard techniques. But also, we launched Chinese, Mandarin, Cantonese, Japanese, Korean, French, Italian, German, even some languages in South Africa. We had an intern who was interested in that to bring voice search and mobile devices to different communities in South Africa, so he did Zulu and Afrikaans. We also, since we launched, we cut the number of errors in half and reduced the latency substantially. So it's really important to be fast. So it should be faster than typing, otherwise I would just type. Also, we noticed that with increases in accuracy, And in speed, that increases our user retention. So we know if when users come back, we know when users search more often, and we can see clear trends as we launch new models with better accuracy and that are faster, the users return. So in the next part of the talk, I'll give a brief overview of the recognizer behind Google Search by Voice. The recognizer is also built at Google from the ground up, and it depends heavily on the finite state transducer library, which is developed jointly by Google and NYU's Courant Institute. And the library is open source, so anyone can actually download it. It's called the OpenFST library. I'll not spend too much time describing the recognizer. There's plenty of books and resources, and probably many people know exactly how it works. But one can download also the HTK toolkit from Cambridge University. We have lots of people working from Cambridge University, actually, in our office. And so all these tools are available. Oh, sorry. OK. So a typical recognizer works as follows. A voice signal comes in. So this is the voice signal. We compute features every 10 milliseconds from the incoming audio. So these features model the spectral information. Essentially, it's a Fourier transform. Next, the features are mapped on a sequence of symbols or phonemes, which we model using hidden Markov models and Gaussian mixture distributions. Okay? And the aim of the recognizer is to decode the audio into the most likely sequence of words using the language model. So we get the features, we compute context-dependent phonemes. Those are turned into phonemes of the language and then into words. So I'll go into these details. So for example, finite state theory. So we use finite state theory everywhere and provides a framework where we can use standard graph construction and optimization techniques to incorporate the knowledge sources that we have. So if we start from the back here in this sequence with G, which is the language model. So here we have a probability distribution over sequences of words. So once I say books on Barnes, the probability is really high. I'm going to say andnoble.com, for example. So we model the probability distribution, and we extract this probability distribution from the query stream, and I'll talk about that a little more, and tries to capture the words, phrases, and sentences the people will say along with the probability that they will say it. And then moving one back to the lexicon. So here we fold in the pronunciations of the words through this lexicon, and it defines the sequences of phones or basic sounds of the language that will get strung together to create the sounds of the words. Okay, so the lexicon is not as complicated or interesting as the language model. And then I'm going to head to the acoustic model now. So looking back at the first description, remember we create features every 10 milliseconds. Those are the encode the spectral information. And the acoustic model tries to capture the variability of phones in the language. We model phonemes in a standard way in the context of their left and right phonemes. So these we call triphones. And it makes the job of the acoustic model easier. And then the C, which is the context dependency transducer, maps triphones, maps basically the context-dependent triphone. So for example, the A in the word cat and the A in the word bat to the sound A. And after that, the phonemes, that goes to the lexicon puts them together, and that goes to the language model to put the words together. And using the composition operator, which I'll just show you an example of what it does soon in the FST library, we can fold all these sources together, build graphs, and search these graphs in an efficient manner. So ultimately, what you get out of here, out of putting all this data together, is a very large graph. And our task is to search this graph. And again, all these algorithms, not the search, or some of the search algorithms, but the composition algorithms, the minimization algorithms for these graphs are available in the OpenFST library, and we use exactly the ones that are open source. Okay, so to graphically illustrate them, so this is a small language model that consists of the phrases Jim read, Jim wrote, Jim fled, and the same for Jill and Bill. You can see how we encoded these 9 possibilities in this small graph. And this is the actual output from the draw operation of the FST library. These here, the numbers, are negative log probabilities, and these are conditional probabilities. So if you say Jim, then you can add these probabilities together to see what is the probability after you say Jim to say Jim wrote. I mean, of course, I say these are probabilities. These are negative log probabilities, so we don't have probabilities greater than 1 in our models. So that was the language model we're going to work with in this example, and here's the pronunciation model. So the pronunciation model starts from this initial start state, says if you start with a B, then you're going to say Bill, and what the sounds that are going to follow are IH, L, and end marker. And then we have a free transition back to the beginning, so you can loop through this. Okay. So you notice this is highly non-deterministic. Starting from state 0, you can go anywhere, and this is extremely difficult to search. Okay. So then next we compose with the language model. Okay. After composition, we have a transduction or transformation of phonemes to words that encode the pronunciation of the words, as well as the structure and the weights of the language model. Okay. And one problem is that the size of the composed transducer is prohibitively large. So what do we do? I mean, here I'm showing you the end result, but it doesn't. I'll show you how it looks like through different stages. So using FST algorithms, we can minimize the transducer. And recall they were non-deterministic, and what you see here is actually a deterministic graph where if you say Bill, then you're definitely if you start with a B, you're definitely going to say Bill, because that's the only choice we have in our language model. And using these techniques, we're able to create, again, like I said, a recognition transducer that encodes all the knowledge in the query stream in one giant network. And it's really a giant network. So searching it is hard, and we'll talk about how do we search it and how we prune. So here's what happens. So remember, this is our graph. I just put it here down for reference. When we first compose it with the lexicon, you get essentially the pronunciation of this part of the graph, and then followed by the pronunciation of that part of the graph, and this is how it would look like. When I determinize, now I start from a non-deterministic, we call them machines or automata, to a deterministic one, and notice now that Jill and Jim have been folded into one edge with the probability of the minimum of the two. And once I start discriminating between Jill and Jim, well, Jill gets probability 0 because all its probability is in the beginning of the transition. And if you add this number and this number, you get the number for Jim. Okay, so this determinization algorithm, again, is open and available. And then minimization gets rid of extenuous transitions. So for example, all these epsilons, we can fold them into one transition. These epsilons here, they can be folded into these two transitions. I think this is provably optimal, if I'm not mistaken. Okay, so any questions so far, or shall I continue? Please.
Just to know about the size of the graph, would be very complex?
The graph is extremely large and very complex. And imagine taking a million, I mean, I'll talk about it a little bit. Imagine having a 1,000,000-word vocabulary and training on 230 billion words, and building it from a query stream of 6 months or a year. That's how big it is.
Do you actually generate and store the graph?
Yes, with all its probabilities. So we actually have, because it's a huge graph, we had to come up with compression techniques to compress the graphs, and that was a paper I published with a few colleagues, and it's part of the resources at the end.
This work of all search engine like Google.com, because https.google.com is different from Google.com.
This is specific to voice search. voice. This is, I'm giving an example in English.
http.s.google.com and http without s, google.com.
Audio is transcribed. The final system has approximately 400,000 parameters. So the takeaway from the slide, I mean, we use the standard techniques so far, that we are training on a large amount of data with large models, but using standard techniques. And this is enabled by our computing infrastructure. Okay? However, lately, because we're getting 1 to 2 orders of magnitude more data than what we have right here, so 1 to 2 orders of magnitude more than 1,600 hours of speech, supervised training is no longer scalable. So, you know, we've been using, like I said, the typical state-of-the-art technology, collect a bunch of data, transcribe it manually, and apply the usual alphabet soup, LDA, STC, MMI, boosted MMI. But a big change is happening. So we're getting more data, and we cannot transcribe it anymore. It's very time-consuming, and it's very expensive. And so the big challenges from machine learning perspective, and as well as system infrastructure perspective, is how to deal with essentially unlimited data. Most systems are trained with a few thousand hours of speech, as you know, and even that's if you have lots of access to audio. But if you get 2, 3, 4 orders of magnitude data, how do you use it? What do you do? And so what we're doing is research in unsupervised training, online algorithms, and so on. So this is an active area of research, just enabled by the fact that, I mean, this is data that people have not thought about handling before. Maybe the US government did, but no one else. Okay, take advantage of all the data. We need to make our models richer. So in order to be able to understand the knowledge embedded in our data, when you have that much more data, we need to increase the number of the parameters in the model in intelligent ways. So our research is not only on supervised training in the sense of how we use the data, but also how do we grow our models in the best way as the amount of data increases. And we use, you know, in order to work with all this data, we use the MapReduce framework for training. And tomorrow I'll talk about MapReduce, so you'll get an idea of how we parallelize things and how we do things on using our computing infrastructure. But that's it about the acoustic model. Most of the innovations so far we've had were in language modeling. Acoustic modeling, like I said, so far just using standard techniques with data, and we're thinking about how to use, you know, because voice search has been fortunately successful, more and more people are using it, and we don't know what to do with the data. So acoustic modeling has been, now it's going to the next challenge, but in language modeling, we're already there. We were there from the beginning. Okay, and one problem, it's not a problem, the problem we're trying to tackle is that the queries are not limited to any domain, like I said. So there's weather, there's URLs, there's geolocations, and I showed some of these. And the main thing, because we trained from the Google query stream. So initially, we took a big gamble. We said, okay, we want to build a large language model. You need to build a voice search system, and you need a language model. But in order to get a language model that's fits the problem, you need to have the system to begin with. You need to collect the data. So what do you do? So it's a chicken and egg problem, and we took a big gamble and said people will speak to the phone the way they write to Google.com, and that's not very clear. A priori, it is not clear. But even if you assume that, the way people speak something is different than the way people say something, the way people write something. Okay, so the first task we have is text normalizations. So, for example, when you type bankofamerica.com, you say bankofamerica.com. Heroes and NBC.com. I mean, the only way to say NBC.com is this. And so our first task is to take the written query and normalize it, transform it into a spoken query. Pretend that this is what people spoke into Google.com. So here's how a process works. So text normalization in general is an ambiguous problem. So what we do is we get the query, we annotate it, we say, okay, this $20 is a currency, Amazon.com is a URL. And once we know this, the task is much easier. We can then go through multiple normalizer. The time, date, number normalizer knows how to deal with $20. The URL normalizer knows how to deal with Amazon.com. And these models can either be, I should probably go to the next slide. So these models can either be statistical based or rule based. So for example, the number one is a rule based model. It's not a model, it's a rule based normalizer. And the URL normalizer is actually statistically built. So the way we built the URL normalizer is we find all the queries that are tagged with URLs inside them in the query stream. We take those and we break them up into all possible constituent words in the normalizer. And there are some ambiguities because we don't have spaces to separate the words. Then we run those back into our language model to see what is the highest probability of these sequence of words. And then we say, okay, this is the output, and we take out all the URLs from our language model. So all we keep is the constituent words of URLs. And because we use the FST library, so how do we do this in FST? So this T is an acceptor that given written text, it basically represents written text and says, okay, this is how I represent this URL, for example, as its constituent words, and then this normalizer changes them from written to spoken. And because we use the FST framework, we can take this automata, T spoken, reverse it, and we get the inverse. So now when I say barnesandnoble.com, what you see on voice search goes through the inverse normalizer, and you get barnesandnoble.com. So we train on the spoken queries, and we try to show to the user a written query. Switch, please. I'll give an example of this. They say never do something unrehearsed, so I have them written down here. 16th Street and 8th Avenue, New York. So I'm hoping this is just a network issue. So this is a network issue. So I'll try it and I'll cancel that job. 16th Street and 8th Avenue, New York. Okay, so this is, okay, maybe it is a query. Heroes DVD on Amazon.com. Notice I didn't just have to say Amazon.com, so the URL can be embedded inside my query. But I don't think I have a good Wi-Fi network. So what you see is what you expect. 16th is actually 16th. 8th Avenue, interestingly, remains as 8th, the word 8th, because avenues in New York sometimes are written. So people actually write 8th Avenue in the query string. And here's DVD on Amazon.com. Amazon.com becomes the URL. Okay, so sorry, switch please. Okay, so in acoustic modeling, we are slowly getting to the point where we can talk about unlimited data. But in language modeling, we're already there. So as you can see in some of the slides, this makes a big difference. But just to give you an idea of the numbers, like I said, we train on about 230 billion words. Those are all spell-corrected queries, also normalized. This requires 70 CPU years to process the data. And this is done, maybe it's more often now, but weekly or... eventually we trim the vocabulary because otherwise it's enormous. And we keep 1 million words. The out of vocabulary rate is 0.57%, which is great. Okay, and as you know, so we want to measure error. And as you know, perplexity is, crudely speaking, a measure of the size of the set of words from which the next word is chosen, given that we observe the current history. So basically, the lower the perplexity, the lower there's variability and the better your acoustic model. The word error rate is clear. It's 100% minus the number of substitutions, insertions, and deletions. And finally, we have a new measure, because this is actually what matters for our users, WebScore measure. So we say, given the actual, what was the intent of the user, and given what we transcribed, how many of the top results did we cover in the results that the search engine returned? So it's basically a covering type of score. So really, it doesn't matter if we misrecognize things. As long as the search engine gets it, as long as the user gets what they want in the results that they see on the screen, that's what matters. And so we try to measure that with the web. So even coming up with this measure, when I describe it, it's trivial, but coming up with it was also a challenge. And we see that word error rate and web score are very highly correlated. And they also substantially decrease as a function of the size of the language model. This is log scale 10 to the minus 1 billion 5 grams. So here we're talking about, this is 1 billion basically, and n grams. And also, we also see an excellent correlation between perplexity and word error rate. And if people familiar with the field, those are usually weakly correlated. And in results that are shown in the literature, those are, people say perplexity is not a good proxy for the word error rate. But in our task, but it could be either because of our task, but more likely because of the amount of data we are using, the perplexity becomes a good measure. So this was surprising when we showed this in conferences. This is surprising. Okay, so that's it for the recognizer, but as you saw, the user interface, that's just half the picture. The other half is the user interface, and it can basically make or break the application. And there are many interesting problems for UI designers, and even the UI is data-driven. So for example, we can always publish to different UIs, see what works better based on the clicks, and then do these A/B experiments, and then come up with a better UI. So even the UI is data-driven at Google. There are many basic questions that on the surface seem simple, but they also require lots of work. What does the button look like? Where do you place the n-best list? So, for example, you saw that I got an n-best list, but another thing is if I press the result that I get, you also get another n-best list. And I don't know if this, I won't try it here, but Jordan, for example, the word Jordan in our language model is a little ambiguous. If I say capital of Jordan, what I get as the first result is what's the capital of Georgia. And in fact, when I tell people, they ask me, where are you from? I say Jordan, they say, oh, you're from Georgia, you're from Russia. And so even humans make that mistake, and our second option in our language model is Jordan, usually comes out. If you say Jordan, it comes out correctly. And so how do you display the n-best? We call it the n-best list. How do you display it to the user? And also, for example, on the iPhone, in the first version we produced, we take advantage of the fact that there were accelerometers and a proximity sensor. And once you raise the phone and put it towards your voice, if you have the voice application up, we detect the accelerometers, we detect the proximity, and we give you a little tone saying you can speak now, basically. It's a little beep, and once you speak, it does the search. So no buttons on the iPhone. It makes mistakes, and we've played with different ways of doing it. Some were rule-based, some we trained models, again, to say what is the right triggering point. And so that was also a fun project. I talked a little bit about the alternates UI, because we make mistakes, and we make a lot of mistakes. And so so mistakes are okay as long as the user can correct them, or even better yet, if the search result gives you the better answers, the right answers that you're looking for. So searching by voice is powerful, but there are many circumstances where you want to take action based on the search result. So in the US, we have turn-by-turn navigation. And now you can dock your Android phone in the car, so then we'd like people to be able to say, navigate to, and then an address. And so you can actually do that. We have these keywords that you can use. And when we model them in an FST, essentially it is transitions in the model. That if you say navigate to, we issue a command, and then that leads into the main language model, and you can navigate to anything. You can navigate to Xbox 360, but that's not going to get you places. But some queries, you can do all this, send a message to Rich. You can follow it by immediately in the same sentence, subject, body, and you say the subject, you say the body, and it tries to actually compose the text message as such. Call John at home, because John may have a mobile number too, so that will call his home phone number. Queries like go to Pizza My Heart is actually ambiguous. So do you want to navigate to it? Do you want walking directions, because now we have walking directions? Do you just want the map, or do you want the website? So that's still difficult. And so beyond search, over there, like I said, we have these keywords. We hand-coded these keywords, which is great, kind of works, but ideally we would detect what the user is trying to do, and we would train models on what the users expect that should happen when they want to when they search using the phone. So if someone says open the barcode scanner, we should understand there's an application called the barcode scanner, and that's what you want to open. You're not searching for the text open the barcode scanner, because it doesn't make me a lot. It may be kind of hard, but with Android 4.0. So anyway, the challenge is we want to make speech like search, say something reasonable, and we'll narrow it down to a few choices. We want to learn from users, we want to personalize. So right now, for example, how do we, when you say call John, what if John is not one of your contacts? So actually for your contacts, we package your contacts. If you check the box that we can actually search your contacts, we package the contacts, of course without phone numbers or anything. We send them to our database, and we build a small language model that's personalized for you, so that when you when you try to search, we load up that language model quickly and use it to detect contacts. Other things that we're trying to do is store small information so that we can adapt the output of the models, adapt the models on the fly so that your phone is somewhat speaker dependent, and this way it gets a little better accuracy. So these are some of the personalization features that were coming up. And finally, I wanted to show Another example, hopefully this will work. Okay, let's try again. Switch. So I'll say, so now we have a button in Android that's integrated that you can just press that allows you to speak in any field. So I'm speaking the subject field of a text message. Hi, meet me at a cafe on 36th Street. Let's have some lunch.
You have some background noise going on also.
Yeah, there's some background, yeah. So hopefully the network cooperates. But essentially this gives you, okay, this is not. Perhaps after the talk we can do it live, because this is, I think the network is overloaded and I don't have to charge. Switch, please. We're almost done. So this is what you would have seen. Of course, if I said that text, that's what you would have seen. You don't see that all the time. And so we have APIs for third-party developers to create voice-enabled applications. So in the Android SDK, and you saw in the beginning when last year I talked about Chrome, HTML5 development, you can have a speech-enabled text box anywhere. So we're basically trying to make voice a key feature that's freely available for third-party applications. And also, but if you want to develop your own, you can download the OpenFST library and work with it. And here's just a glimpse of some of the publications that along the way as we were developing the product. The first launch was in 2008, so this is just in the past few years what we've so the second one is the compression paper I mentioned, and the last one is all about the language model and the text normalization. So thank you.
I think a question on everybody's mind is, what about Arab? You're in Arab, you know, a South African came up with Swahili or African. What about Arab?
This is the question.
On everybody's mind.
Yes, so we, I mean, I can't talk about when we're going to launch things or what we're going, but rest assured, Arabic is very important for us. Yes.
About the video, the Chubby Bunny video. So
We had nothing to do with it.
yeah, sure. But I mean, if those kids, they started, the first query was with their mouths, stuffed with marshmallows.
Mhm.
Does it have to do with, because first it was clear that they said Chubby Bunny,
Yeah.
and then they issued it again with a less clear articulation. And, each time the articulation is less,
Less.
it's not that clear. So
Yes.
does it have to do with, because they are gradually, converting from a very clear articulation to a very not
So
clear?
this is a very interesting sort of session feature, but we actually don't have that. So that's what that was not happening there. But if we did have the adapted models, then their game wouldn't work as well. I mean, not that like the way they want it, because then it would start adapting to their voice slowly. So if one guy wants to win all the time, he would stuff 6 marshmallows and say Chubby Bunny until it gets it right, keeps on repeating until our models adapt to the way he says Chubby Bunny with 6 marshmallows, and then he'll win. But I won't tell him. Yes.
Can we use Google computation power to train our Arabic data?
So no, unfortunately not. But there is a product that was also a product of Google research in New York, where they allow you to run Google classifiers on your data. So, but those are standard. You say, I want this kind of. I think you can pick. I'm not sure, but you can pick a classifier and you have your data. You upload. I think it's part of App Engine, but I'm not sure. I mean, this is brand new. It's out, but it's very new, and allows you to sort of classify. But we don't. You cannot train with your models using our training techniques.
Another question, what exactly the input of your algorithms to perform the training?
I mean, besides you get the voice in 10 millisecond chunks, we break it up, and then we assume the 10 millisecond chunk is stationary, and we do take a Fourier transform on that. And so they're essentially MFCCs, so it's double Fourier transform.
No, I mean, not the testing data, the training data.
The training data is, I mean, it's initially bootstrapping into something, but imagine you have the system now, okay? And so you have the queries coming in. So you take these voice queries, and we actually have people transcribe them. So this is for the acoustic model, of course. We have because for the language model, we just use the query stream. But of course, anything transcribed from the spoken query stream, we can also use it. Once we get those, we do the forced alignment and train the acoustic model. And so, but again, like I say, this is no longer scalable anymore.
Again, about Arabic, when you said Arabic is coming soon or whenever, you talk about traditional Arabic or the original Arabic?
Very interesting question. I don't know, because if you're searching for a news article, what would you use? Standard Arabic. But if you're searching for a song, what would you use? So you would use the colloquial. So these questions are, what if you're mixing the two? What if you're searching for a URL in the middle? So then now English is mixed in, right? And so you can see where it's coming. And besides standard and colloquial, it's standard and multiple colloquials that are very, very different. I mean, this is not the difference between Australian English and US English. It's much more pronounced. Please, last question at the end.
So will this service of voice query be available through our website, or just be restricted to smartphones?
I think Sebastian showed something with HTML5 where you can embed any text box in there. So it should be coming elsewhere, but right now it's just on smartphones. Essentially, we didn't see the big benefit in sitting on your computer and talking out search queries. People type much faster than we can send this data out to the server on a keyboard. The problem is with these smartphones, you're typing on a screen, and it makes lots of mistakes. And I mean, even on the BlackBerry, it's not a clear-cut case, right? The BlackBerry, you can type extremely fast on it. So, so that was, we always had these tests. I'll say something, you type something, and who wins? And sometimes it's the person who types, sometimes it's the system. So it's not very clear.
Right, thank you, Bolus. You will be available for questions during lunch or afterwards.
Yes.
On the demo pods. So thank you very much.
Thank you.
So just two things. I think we forgot to give mugs to people who ask questions.
Yes, I did.
So you can maybe go to Bolus, who will maybe remember who asked questions. Enter questions. Well, come with me then afterwards.
Okay.
And second thing, so now it's lunch break. We'll start again at 2:30, not 2:15, so you have a bit more time to eat because we're slightly late. So 2:30, I think back into the main room, or maybe we have parallel sessions as well. But I'll make a